share my screen. Where is, he's not around today. Okay, so you are his assistant today. You know, he always checks for us. Everything is proving to be slow. Is it showing? Okay, so we are going to look at the assumptions today. Where is Microsoft Word? I'm gonna write something. My computer is slow. We are going to start with multicollinearity, and we'll look at omitted variable bias, which you already know. After that, I think we should look at normality, and we'll look at heteroscedasticity, and then we'll look at autocorrelation, and we'll look at stability diagnostics. By the way, guys, I'll explain all these things. Under stability, we'll look at Ramsey test. Okay, so we'll look at multicollinearity, and we'll see omitted variable bias. Then we'll check residual diagnostics, normality, heteroscedasticity, autocorrelation. These three assumptions are related to the residuals, so they are residual diagnostics. Then we'll check stability diagnostics, and in particular, we'll look at the Ramsey reset test, which I know this is the only new thing for you. Just this Ramsey test, all these ones you know. Before I get into it, I'm going to show you what I showed you last time, and you know. And the reason I'm showing you this is because last semester I ate a lot, I know. This semester, maybe I'm not explaining a lot. For whatever reason, maybe I'm getting old, you know. I'm getting old, right? So you might want to watch the videos of what we did last semester, which is actually the same thing. It help. You might get more insights. Why is it not coming? Everything is, the computer is slow. I put these videos on YouTube, so you can get it there. By the way, this is my name. You can check me on Teams in case you want. So I post a lot of interesting things here. You can check if you want. It's not compulsory anyway. So last semester we had 10 recorded videos, 10, and I listed them in tutorial, like tutorial 1, tutorial 2, tutorial 3, right up to those are the 10 videos of what we did last semester. So if you look at tutorial 9, it is residual diagnostics, normality, autocorrelation, heteroscedasticity. We did 3 of them in tutorial 9. And I think we had one special session for multicollinearity. Yes, tutorial 8 was just multicollinearity and omitted variable bias. So I think if you can find time to watch this tutorial 8 or tutorial 9, it might help. Maybe I explain something there which I might not explain today. But of course, I'll always try my best to explain. So I'm just saying this kind of things might help. Okay. So we have data. This is carbon dioxide. By the way, this is time series data from 1990 till 2019. Our dependent variable is carbon dioxide emissions, and we have 3 independent variables, or you can call them regressors. We have financial development, which is proxied by domestic credit to private sector. We have economic growth proxied by GDP, and we have urbanization proxied by urban population. By the way, carbon dioxide emission is proxy for environmental sustainability. Okay, so we have dependent variable and we have these 3 independent variables. So I'm going to run a regression. First, I will input this data to eViews. I'll use eViews 10. I like using 10, but you can use 10. You use 13, anyone you have. But I like using 10. So just open eViews, come to create new file. Of course, you see here dated regular frequency because it's time series, annual because it's annual data. So I'm checking, start date is 1990 and end date is 2019. Why are so many things open here? Okay, let's do this one. So 1990 till 2019, right? Now I'll input my data. I'll just type in the command data, then I just write the variables CO2, financial development, GDP, and urbanization. So I'll copy variables and paste. All these things you know. So at times it gets boring. One and the same thing, you know. After today, I'm no longer talking about regression. We should talk about something else, right? So I paste the data on eViews. Let's use a log form. So I'll generate a log form so that we can express everything in percentage. It generates then CO2 equals log CO2. Then here I will just change this CO2 to FD and change CO2 to FD. All these things you know. So I'm just trying to be fast. If there's anything you don't understand, watch previous videos. That will save time. We have our data and I've generated a log form. Now I'm going to run the regression. First of all, let's start with multicollinearity. So the first thing we'll look at is multicollinearity. By the way, what is multicollinearity? Multicollinearity is a situation where your regressors, and by regressors I mean independent variables, where there is powerful linear relationship between any of your independent variables. We don't want it. By powerful linear relationship, I mean it should not be like 80 and above. When you see correlation coefficient is 80 and above, you have to be suspicious of multicollinearity. In some books, they will say 85, some will even say 90, but I prefer 80 because Whenever I see above 80, I'm suspicious of multicollinearity. That's why I don't rely on one method. I use different methods. I check correlation metrics. I check various inflation factor. I try to check the R squared and other things so I can make an informed decision. But we are going to check multicollinearity. So we will check the correlation metrics to make sure none of the independent variables have this powerful relationship. Okay. So, first of all, I will highlight all the variables: lane CO2, lane FD, lane GDP, lane urbanization. Just press enter, come to view, come to covariance analysis, remove this covariance and take correlation. Click OK, and we have the correlation matrix. This is the correlation matrix. So I'm checking these correlation coefficients to make sure none of them is above 80%. But you have to be careful. We are interested in the correlation coefficient among the regressors. It has nothing to do with between the regressor and the dependent variable. Of course, we want a high correlation between regressor and dependent variable because it means there is high explanatory power. But we don't want a high correlation between any of the regressors because if any of these regressors are powerfully related, then you cannot hold one constant while trying to interpret the effect of the other. So we don't want this. So our dependent variable is CO2. So I cannot check this coefficient. Why? Because this coefficient is between CO2 and FD. I cannot check any of these coefficients. Why? Because they relate to the dependent variable. But I will check this one because this one is between FD and GDP, two regressors. And you see it is less than 80. So this one is telling us no multicollinearity. I check this one, FD and urbanization is less than 80. So no multicollinearity. But this one is above 80, problem. There's multicollinearity. The issue with this multicollinearity is that one is enough. You must not have a high correlation with all of them. Just one is enough. So if you have just one of the correlation coefficients among the regressors is above 80, really, really high. For instance, this one is 93. That's telling you that there is multicollinearity. So just one is enough. At times you might get confused while trying to report these results. You might end up reporting these ones, which is between the dependent and independent.
We need to take out from the model for the one independent in this case.
Sorry?
We need to take out one independent, which gave us a multiple.
Yeah, I'll tell you how to solve it. Sure, that's one method to solve it. Yeah, there are other methods. We'll talk about it. So what's happening in here is that this is the only coefficient which is problematic for us. Okay, you see all these 80, 86, they are above 80, but they are not problematic. Why? Because it is between regressor and dependent variable. For multicollinearity, we are not checking between regressor and dependent variable. We are checking only among regressors. So instead, these ones are high, we are happy. We want the regressor to have high explanatory power on dependent variable, so we are happy. But we are not happy with this. We don't want the regressors to be related that much. So in order to avoid this problem of mistakenly interpreting regressor and regressor, what you can do is you can check correlation metrics in such a way that it will not show you dependent variable. It will show just independent variables. How can you do it? If you want to do it, come to quick, come to group statistics, right? Come to correlations, and then here, type in just the regressors. So I'll remove this dependent variable. It means it will show me correlation just for the regressors. Put just the regressors here. So you see this is correlation matrix, but now it is just for the regressors. So you can confidently interpret these coefficients. So you see these two, no problem, but this one, problem. So we found multicollinearity, which means there's a problem. Now, another way we can check that's one way to check multicollinearity, the correlation matrix. Maybe I should write it down. Correlation matrix. And as a rule of thumb, we don't want any of the correlation coefficients to be above 80. We can also check multicollinearity using variance inflation factors, IF. Now, unlike correlation metrics where you can just directly check the correlation, with variance inflation factors, you have to run a regression before you can check it. So, what do I mean by that? I'll run a regression. So quick, estimate equation. I'll put my, you know how to run regression, right? Ln CO2 constant, that is put dependent variable, put constant, and then put independent variables. Ln financial development, ln GDP, ln urbanization. Click OK. This is a regression. Okay, but I'm not interested in checking the coefficients and everything. I want to check variance inflation factor. But you have to run the regression first. Once you have your regression output, come to view, come to coefficient diagnostics, and then you see variance inflation factors. If you click variance inflation factors, you have your results. Focus on centered VIF. Forget about this uncentered VIF. Check the centered VIF. Now, as a rule of thumb, we don't want any of the variance inflation factors to be above 10. Yes. In some sources, they say 5. Some online sources and in some books. But I was taught of 10, so I used 10. So if you look at these variance inflation factors, none of them is above 10. So based on this, you can say there is no multicollinearity, right? At times, you get conflicting results. Maybe correlation matrix is telling you that there is multicollinearity. VIF is telling you that there is no multicollinearity. In this kind of case, always go with the correlation matrix. The correlation matrix is the best, as far as I know. So at times, both of them confirm each other. At times, you get conflicting results, but correlation matrix is good. Like you see, it's telling us that we have 93% correlation. So, and by the way, in some sources, they will tell you that the benchmark for VIF is 5, not 10. So if it is telling you that 5 is a benchmark, then based on this, we can say we have multicollinearity, because you see here we have 8, here we have 9. But I was taught that we should use 10 as a benchmark. So I'm telling you to use 10, but always check both correlation metrics and variance inflation factor. And if you have conflicting results, always lean towards the side of correlation metrics. So this is it. Okay, now another thing I'll tell you is this variance inflation factor, we also have tolerance factor. Tolerance factor. Now, this tolerance factor is actually the reciprocal of variance inflation factor. What do I mean by reciprocal? I mean, if you take, it is equals to 1 divided by VIF. So, if you take 1 divided by the variance inflation factor, it will give you the tolerance factor. And once you get the tolerance factor, if you take 1 divided by the tolerance factor, it will give you the variance inflation factor. So both of them are reciprocals of each other. Okay, now we can also get this tolerance factor by doing auxiliary regression. But I will not show you auxiliary regression because I'm trying to save time. So I'm showing you a shortcut you can use to get tolerance factor. Because maybe in the exam, Nigahoja might ask you to get tolerance factor. Right? To get tolerance factor, you can run an auxiliary regression and you will be checking a root square and everything, and you can calculate tolerance factor manually. But as a shortcut, just estimate your E-views. On E-views, run your regression and get variance inflation factor. Once you get this variance inflation factor, just take 1 divided by the variance inflation factor. It will give you the tolerance factor. It's kind of a shortcut for you.
Yes. We need to divide which one?
1 divided by variance inflation factor will give you tolerance factor. So you can get these variance inflation factors from E-views, right? But E-views will not give you tolerance factor. But how do you get tolerance factor? Just take 1 over the VIF. It will give you the tolerance factor. Because tolerance is the reciprocal of VIF. You understand? Okay. Now, with this tolerance factor, how can we use it to decide with multicollinearity? We don't want tolerance factor to be close to 0. We don't want VIF to be very high, and we don't want tolerance factor to be very low. If VIF is very high, like 10 and above, we say there is multicollinearity. If tolerance factor is very low, that is close to 0 or even 0, if tolerance factor is very low, close to 0 or even 0, it means there is multicollinearity. If VIF is very high, like 10 or above 10, it means there is multicollinearity, right? So it's like the reverse. With correlation metrics, we don't want it to be, correlation coefficient to be like 80 and above. With variance factor, inflation factor, we don't want it to be like 10 and above. With tolerance factor, we don't want it to be very low or close to 0, because these kind of things indicate multicollinearity. Okay. Now, if we check and we have multicollinearity, now how can we solve multicollinearity? Because if there is a problem, we have to try to solve this problem, right? So how can we solve multicollinearity? That's the next thing. Solution. Solution. Now, there are many ways we can solve it. First, we can try using, I'll explain, a different proxy. Of course, we can always try log transformation. It always helps. I'll explain. We can try using a different proxy. We can try dropping problematic variables. We can try ratio transformation. There are many methods. I'll tell you just about these 4. Okay, if we find multicollinearity, how can we solve it? First of all, always use log transformation. You see, I'm using log here, right? Always use the log form, because logarithm is good. It tries to solve so many problems. It rescales the data, reduces the variability, and it is trying to solve so many problems. Multicollinearity, heteroscedasticity, autocorrelation, even normality. It's trying to solve so many problems. So always try to use log. So in case, let's say you're working with data which is level data, not log, and you find multicollinearity, go back and try to use log. Maybe it might help. It's not a guarantee, but it might help. So that's one possible way. Another possible way is maybe try using a different proxy. Like if you see here, our variables we are using is carbon emissions here. Okay, multicollinearity has nothing to do with dependent variables, so we'll forget about carbon emissions. So we have these 3 variables. Domestic credit to private sector. By the way, this is a proxy for financial development. GDP per capita is proxy for economic growth. Urban population is proxy for urbanization. So let's assume that this domestic credit to private sector is one of the problematic variables. It's one of the variables which is causing multicollinearity. So maybe try to use a different proxy. You know, for financial development, we have many proxies. You have the IMF's Financial Development Index. you have domestic credit to private sector, you have different proxies, maybe market capitalization. So try to use a different proxy for the same variable. Maybe if this particular variable is causing multicollinearity, but just change it, maybe go and download different data and use a different proxy, but it's still financial development. Like, let's say you're trying to measure financial development here, so you're using a proxy. This domestic credit to private sector is a proxy for financial development. But in this model, if it is causing multicollinearity, try to use a different proxy. Maybe you should use the financial development index from IMF, which will still be a measure for financial development, but maybe it might not cause multicollinearity. Or maybe you can use market capitalization. There are different proxies. So try to use a different proxy for the same thing, the same variable. It might help. Or if it does not help, another thing you can do is you might consider dropping one of the problematic variables. So let's assume that we have a problem between this financial development and this economic growth. Let's say these two variables have a high correlation. They are causing multicollinearity. And you try using different proxies, it does not work. So maybe you should consider dropping one of the variables from the model. Maybe remove it. But why, before dropping one of the variables, you have to be careful. What do I mean by careful? Maybe the theory says this particular variable has to be in the model. Maybe you're doing a study based on a theory, and the theory is telling you that this particular variable has to be in the model. Then you cannot drop that variable. You understand? You cannot remove it, because according to the theory, it has to be there. Or even if the theory does not say you should drop that variable, maybe out of intuition, maybe you check so many studies, they are using this variable, so it means it's an important variable which has to be in the model. And if you drop this variable, you might cause a problem which is called omitted variable bias. So initially we have a problem, multicollinearity. We are trying to solve this problem by dropping one or more of the problematic variables. But you have to be careful. Why? Because by dropping this variable, you might cause another problem which is known as omitted variable bias. That is the reason why whenever you try to solve multicollinearity by dropping a variable, you have to always test if you have caused another problem, which is omitted variable bias, because you might solve this problem by causing another problem, right? So you have to always be careful when you drop variables. Okay, I'll come back to it. Another method is ratio transformation. I rarely use this one. I've never used it, but I'll explain to you how it works. So let's assume that, let's say you have two variables, GDP, and you have population. Let's say these two variables are regressors in your model, and they are causing multicollinearity. If you use both of them as two separate regressors, they are related, multicollinearity, but you don't want to drop any of them. You want to incorporate the effects of both of them in the same model. You try using different proxies, it's not working, and you cannot drop any of them because you want to make sure both of them are there, but both of them are causing multicollinearity. So you can consider combining them to form one variable. You can combine these two variables to form one variable. So what you can do is you can take this GDP divided by population, and it will form a new variable which is known as GDP per capita. Yes. You know, per capita means divided by population. So if you take GDP divided by population, it will give you GDP per capita. You can now use this GDP per capita as a single variable. You understand? So this GDP per capita it's a single variable, but it will account for both GDP and population, because you want to have the effects of both of them. You don't want to drop both of them. So it helps. These kind of things also help. Okay, I will come back to this. Let me come back to this dropping problematic variables. So again, if you drop problematic variable, you might cause omitted variable bias. So you have to test for the omitted variable bias. So I will show you now how to test for omitted variable bias. No, omitted variable bias is only when you drop a variable. Yes. If you drop a variable, you should test if by dropping that variable you have caused omitted variable bias. Okay. So now, what is happening in here? By the way, we found which one is okay. I will do it again. So lean CO2, lean FD, lean GDP, lean urbanization. I want to check correlation metrics again. Okay, so you see here there is problem between GDP and urbanization, 93%. So GDP and urbanization, they are causing multicollinearity. So I have to drop one of them. That is where you can try checking using different proxies, or you can try other solutions, but let's assume that they don't work and the only option for us is to drop one of them. So between GDP and urbanization, I have to drop one of the variables. You don't just drop them. You don't just guess and say, I'll drop this one. How do you know which one to drop? Okay. Run a regression with all the variables. Run a regression with all the variables. Let me show you. Lean CO2, constant, lean FD, lean GDP, lean urbanization. So it is GDP and urbanization which is causing problems, right? So focus on those two variables. So I will run a regression with all the variables. Then now I'm focusing on just GDP and urbanization. Between both of them, check their statistical significance. That is, which of them is least statistical significant. GDP, anyway, both of them, none of them is really significant. But of course, one of them is more insignificant than the other. So you see that urbanization is more insignificant than GDP, right? So in this case, we should drop urbanization. That is, there are two variables I'm considering to drop one. So which of them should I drop? Run a regression with all of them. The one which is least significant or the one which is more insignificant, that is the one you should drop first. So since urbanization is more insignificant, I will drop urbanization. Okay. Now, I will run my regression now without urbanization. Lean CO2, constant, lean FD, lean GDP. So I'm not putting urbanization. I run the new regression, right? If I run this new regression, when you run a new regression without urbanization, which we have dropped, what you have to do is check again if there is still multicollinearity, because you have to be sure you have solved this problem. So I'm checking again correlation metrics. Okay, I'll check variance inflation factor. Of course, correlation metrics is still the same thing, so but let's just check variance inflation factor. So you see it is now low, 2.3, 2.3. So there's no multicollinearity. Okay, now I have to check to be sure that variable I have removed has not caused omitted variable bias, urbanization. So how do I do it? Come to view when I have this regression output, right? Remember, this regression is without urbanization. So come to view, come to, let me see, look for it. Yes, come to coefficient diagnostics. Come here to omitted variable tests, likelihood ratio, omitted variable tests. Click on it, and here just type in just the variable that has been removed. The variable that we removed was urbanization, right? So I'm just typing here lean urbanization. That's all I'm typing. If you remove more than one variable, type in both of them. But since I removed just one, type in just that variable which has been removed, and then click OK. You have this result. In this result now, we will be able to test. I think the null hypothesis is written there. This is a null hypothesis. Urbanization is significant. That's the null hypothesis. So the null hypothesis is telling us that null telling us that lean urbanization is significant. Insignificant, I think, is insignificant. Therefore, what will be the alternative? It's telling us that lean urbanization is significant, right? You don't even need to cram it because it's written there. So, is it significant? Lean this is significant. Oh, significant. Okay. So here is significant, and here is insignificant. Insignificant. Okay. So check. You can check the T statistics or the F statistics. Anyway, the T and F statistics will be the same because it's just one variable. But in case we remove more than one variable, then we might have T statistics and F statistics different. So for me to be on the safe side, always check F statistics. Don't check T statistics. But you need T statistic is showing you significance of individual coefficients. The F statistic is showing you the joint significance. So in these cases, it is just one variable we removed. That's why our T and F are the same. But in case you remove more than one, T and F might be different. Of course, they'll be different. So just always check F, forget about T. So we have F statistic, check probability value. What's probability value? 0.39. It's bigger than 5%, right? Which means it is insignificant. We cannot reject. So we cannot reject this null hypothesis. What's the null hypothesis? That variable urbanization is significant. And probability value is bigger than 5%, which means we cannot reject. So if we cannot reject this null, what is it telling you? It's telling you that we cannot reject this null. The null is telling you that that variable which you have removed is significant, and you cannot reject the null. It means that variable is important. You should not remove it. Go back and put it. Right? So, because if you remove it, then you will cause omitted variable bias. But if you reject this null and you accept the alternative which is telling you that that variable is insignificant, then it means there is no omitted variable bias, so you can remove it, no problem. You get the point? So since there is omitted variable bias, it means go back and put back the variable, and maybe you can remove the other one, GDP. If you remove GDP, come and repeat back this process. So whenever you remove a variable, always check if you have created omitted variable bias. Because it makes no sense to solve a problem by creating another problem. So try to solve a problem without creating another problem, right? Okay, if you understand that, then I can say I'm done with multicollinearity. So we have seen how to check multicollinearity using correlation metrics and variance inflation factor. I've showed you how to calculate tolerance factor using variance inflation factor, and I've proposed to you some solutions on how to solve multicollinearity. Dropping variables should be last resort. Try it as a last resort. Always try. First of all, log transformation might help. Try using a different proxy. If the worst comes to the worst, try dropping variables. But before dropping a variable, check the variables which are causing this problem. Run the regression with all of them. Check the one which is least significant. Drop that one. But whenever you drop a variable, always check if you have created omitted variable bias. If there is no omitted variable bias, you can drop it and you can continue. But if there is omitted variable bias, then you have to go back and put that variable and try dropping another one. And then still check again, and so on. Okay, so that's the issue with multicollinearity. After that point, we can look at, so I'm deleting this. Now, we can check residual diagnostics. Okay, now guys, with multicollinearity, it related just to the regressors, independent variables. Now with this residual diagnostics, it is residual diagnostic. Why? Because it is relating just to the residuals, error terms, right? So I'm going to write the hypothesis. By the way, for normality, we are going to use Jack-Berra test. For heteroscedasticity, we are going to use 5 different tests. 5. We have the white test, which is a general test, right? We have the Bush-Pagan-Godfrey test. We have the Harvey test. We have the Gleichzart test. And we have the Ash test, autoregressive conditional heteroscedasticity. This Ash test is not too important because we are not doing high frequency data. But I will just show you that when we'll be doing volatility, it will be very important because it's mostly used when there's high frequency data. But I will show you all 5. For autocorrelation, we'll do 2 tests. We'll do Debin-Watson test, and we'll do Bush-Godfrey LM test. Okay, so these are the tests we'll do. Now, first I'll write the hypothesis. So for normality, what's the hypothesis? These things you know. Hypothesis is that residuals are normally distributed. Null hypothesis is that residuals are not normally distributed. For heteroscedasticity, null hypothesis is that there is no hetero, I don't like spelling this thing, scedasticity. Either you say there is no heteroscedasticity or you say there is homoscedasticity, right? Because if there is no heteroscedasticity, it means there is homoscedasticity. It means the variance is constant. Heteroscedasticity means variance is not constant. Homo means it is constant. Alternative means there is heteroscedasticity. With autocorrelation, null hypothesis is telling us that there is no autocorrelation. Alternative is telling us that there is autocorrelation. I want to tell you something. Okay. After residual diagnostics, we'll see stability diagnostics and we'll see Ramsey reset test. In this stability diagnostics, let me just write the hypothesis as well so I can be fast. Functional form is appropriate, while alternative hypothesis is telling us that functional form is not appropriate, right? Okay. Guys, one more thing I'll write. I want to tell you something. T-test, null hypothesis, coefficient is insignificant. Alternative, coefficient is significant. Why am I writing all these things? Is because there is a tendency for you to cram this hypothesis. I can assure you I used to cram these things. But later on, I was told not to cram it. You don't need to cram this hypothesis. It's for most of the hypotheses in econometrics, the null hypothesis is telling you that there is no problem. and the alternative hypothesis is telling you that there is a problem. Look at normality. Null hypothesis is telling you that it is normally distributed, which means no problem. Alternative is telling you that it is not normally distributed, which means problem. Here, heteroscedasticity, null is telling you that there is no heteroscedasticity, which means no problem, because we don't want heteroscedasticity. Here, there is telling you that there is heteroscedasticity, which means problem, right? Same thing here. No autocorrelation, because we don't want autocorrelation, so there is no problem. And here, autocorrelation, which means problem. With stability diagnostics, here, functional form is appropriate, which means no problem, because we want it to be appropriate. Here, it is not appropriate, which means problem. So you discover that for most of this hypothesis, for most of these tests, the null is telling you that there is no problem, while the alternative is telling you that there is a problem. Yes, I'm going to mention that. Except for t-tests and f-tests and a couple other tests, but typically t-tests and f-tests is the reverse. Null is instead telling you that there is problem. Insignificant means problem. Coefficient alternative is telling you that no problem. And it's the same thing with f-test, because f-test is the same thing, but it's a joint test. So just put it in your mind that apart from t-test and f-test and some other tests, which we will see later, but in terms of the main test which we always see, apart from t-test and f-test, for most of the other tests, especially these diagnostic tests, the null is telling us that no problem. Alternative is telling us that problem. It's easy for you, right? Okay, so we can now do these tests. Guys, to do any of these tests, you must run the regression. You remember variance inflation factor. Before we check it, you must run regression. To do any of these tests, you must run the regression, because you are checking this once you have the output. So this is our regression. So I'll run the regression, quick, estimate equation. So I'll write lane CO2, constant, lane financial development, lane GDP, lane urbanization. Estimate. This is our regression output. Once you have this regression output, come to view, and you can check. You see, yes, residual diagnostics, right? We can check normality, autocorrelation, heteroscedasticity, and stability diagnostics. We can check Ramsey reset tests, right? Forget about all these other tests, all these CHO tests. You will see them later at PhD level, but I will show you Ramsey reset tests. Okay, so let's start with residual diagnostics. First, let's check normality. Now, if you look at the histogram, it gives you an idea if it is normally distributed or not. But to formally test it, we are checking Jagbera test. Of course, you know, skewness, ketosis, these kind of things are helping. You know, for a typical normal distribution, skewness should be 0, ketosis should be 3, but Jagbera test is combining skewness, ketosis, sample size, and it is coming out with test statistic. So we use this Jagbera test statistic to formally do the test. Now we cannot use this test statistic because we don't know the critical value. So we are going to use probability value, because at least we know our significance levels. We know 1%, 5%, 10%. And we always use 5%. Well, you can use 1, 5, 10, but always use 5 because most people use 5, right? So let's use 5%. Check this probability value, 0.66. This is 66%. It's bigger than 5, right? It's bigger than 5%, right? Okay, I'm telling you it's 0.66, which is 67%, bigger than 5, right? Since it is bigger than 5, what does it mean? It means we are unable to reject the null hypothesis. You know, in order for you to reject the null hypothesis, probability value has to be less than significance level. We are using 5% to perform this test. Our significance level, which is actually our alpha, 5%. You can use 1% or 5 or 10, but let's use 5. And in the exam, most probably, Nigaoja might say use 5. They always use 5. So let's use 5. So because this probability value is bigger than 5%, it means we cannot reject this null. We are not accepting the null, but we cannot reject the null. And what is the null? Residuals are normally distributed. If you cannot reject it, it means we conclude that our residuals are normally distributed, which is fine. We want it to be normally distributed. But if that probability was less than 5, then we will reject this null and accept this alternative, which means it is not normally distributed. Okay. So that's how we perform normality tests, Jagbera tests. Now, come again to view residual diagnostics, heteroscedasticity. Now, we have 5 tests here. We have the Bruch-Pagan-Godfrey test, the Harvey test, the Glacier test, the Ash test, and the White test. I always start with White. What you can do is, you can perform all 5 tests, and you go with the majority. Some of them will tell you there's heteroscedasticity, some will tell you there is no heteroscedasticity, so go with the majority. Whatever the majority tells you, conclude. That's what you can do. Or you can report maybe 1 or 2. But if you don't want to report all the tests, if you want to report just 1, then report White test, because White test is the general test. If you want to report 2, report White and Bruch-Pagan-Godfrey, because these are the 2 famous tests. As I know, White is the best, it is the general test, if you must report just 1. But I don't think reporting just 1 is good, because you have 5 tests, so why should you report just 1? Because you know, if you're trying to send your article to a reviewer, and the reviewer sees that you're reporting just 1 test, then most probably the reviewer is skeptical. The reviewer is thinking that maybe your other tests are giving you bad results, that's why you're not reporting them. Because you have 5 tests in front of you, why report just 1? So better report all 5 and then go with the majority. So we'll do it. Let's start with White tests. White tests, we can use cross terms or not cross terms, but for me, I never use cross terms. So this place, don't tick it, remove it. By default, you will find it ticked. So always untick it, but you can still do with cross terms. But me, I don't use cross terms. So no cross terms, and okay. Now this is our results for the White test. Guys, everything down here is not important for us, forget about it. We are directly checking just this probability value. F statistic, this is the test statistic, and this is the probability value. We are not going to use this F statistic because we don't know the critical value. You know, to use test statistic, you have to compare it to critical value. If it is higher than critical value, you can reject. But because we don't know critical value, so we are going to use probability value because at least we know significance levels. So this is the only thing I'm checking. Yes. This is 0.08, which is actually 9%. 9% is bigger than 5%, which means we cannot reject, right? So we cannot reject this null hypothesis, which is telling us that there is no heteroscedasticity. So therefore, there is no heteroscedasticity. But if we were performing this test at 10%, then we will reject because we had 9%. 9% is less than 10. So you see, it depends on what your significance level is. At 10%, we will say that there is heteroscedasticity. But at 5%, and also at 1%, there is no heteroscedasticity. So it depends on your significance level. Yeah, but typically we always use 5%. So White test is telling us that at 5% there is no heteroscedasticity. Let's check the others. View, residual, heteroscedasticity. Let's take Bruch-Pagan-Godfrey. You see, yes, 7%, right? Again, at 5%, there is no heteroscedasticity. But at 10%, there is heteroscedasticity. Okay, let's check the rest. Residual, heteroscedasticity. Let's check Harvey. This is 0.4, 40%. So we cannot reject. So there is no heteroscedasticity. Let's check the other two. Glacier. This is 0.118. That is 19%. Is it 90? Yeah, it's above 5%. So again, we cannot reject. No heteroscedasticity. So 4 tests already is telling us that no heteroscedasticity. So therefore, we can conclude that there is no heteroscedasticity. Normally, we use those 4 tests, but there are 5 tests. This ASH test is not very important for us. Why? Because we don't have high frequency data. This ARCH, ARCH, stands for autoregressive conditional heteroscedasticity. We mostly use it for high frequency data. When we'll be doing volatility, we'll see it. High frequency data means data which occurs, observations. We have many observations in 1 year. You know, with annual data, we have just 1 observation every year. With monthly data, we have observations every month, which means in a year we have 12 observations, right? With daily data, we have like how many days in a year? 300 and something. Yeah, so we have like 365 observations in a year. Weekly data, I think we have like 52 weeks in a year. So we have like 52. So high frequency data means you have many observations in a year. So annual data cannot be high frequency because we have just 1 observation. So we mostly use this autoregressive conditional heteroscedasticity test for high frequency data, like daily data, monthly data, weekly data, maybe quarterly data, I don't know. Okay, but there is no harm in using it with annual data. It's not like you cannot use it. You can use it, but it's not too much important for us. Okay. And another thing with this ASH test is that when using it, you have to specify the number of lags. Now, how do you know the lags to specify? If you are using annual data, right, then you can specify maybe 2 or 3 lags. 2 or 3 lags can be okay. Even 4 lags, no problem, but 2 or 3 lags can be okay. But it depends if you have if you have high observations. That is, if you have many observations, don't use too many lags if you don't have many observations, because you don't have to what we call degree of freedom. I know you have no idea about it, don't bother. But just know that if your sample size is not really big, don't use too many lags. For annual data, you can use 2 or 3 lags. For quarterly data, you can use 4 lags. For monthly data, you can use 12 or 13 lags. It's okay. Daily data, okay, let's not get into that. So since we're using annual data, I will put here 2 lags, or I can leave it as 1, no problem. What happens is that eViews is suggesting for you the lags to use. So at times, no need to change it. Just use what eViews is giving you. But if you feel like there is a need for you to change it, you can change it. So let's use 1 lag and perform the test. Again, just check this. You see, we cannot reject. It's bigger than 5. So no heteroscedasticity. So you discover that with all 5 tests, with the White test, the Bush-Pagan-Godfrey test, Harvey test, Glacier test, and the ASH test, all 5 of them are telling us that we cannot reject the null hypothesis. Therefore, we conclude that there is no heteroscedasticity. So what you can do is, you can create a beautiful table, report all 5 tests, or maybe 4 tests, if you don't want to report ASH tests, or if you want to report ASH tests, report all 5 tests, and then go with the majority. Say, maybe 3 tests is telling us no problem, 2 tests are telling us that problem, therefore we conclude that no problem. But in our case, all 5 tests are telling us that there is no heteroscedasticity. Okay. Now, autocorrelation. By the way, what is heteroscedasticity? I've not even defined it. Yeah. You know, these kind of things relate to the residuals. So, heteroscedasticity is telling us that the variance of the residuals, that is the variance of the error terms, are unequally spread. They are not equal. unequal spread. But homoscedasticity means we have constant variance. The variance of the errors is constant, equal spread, right? Now, autocorrelation. What is autocorrelation? Autocorrelation is a situation where the residuals are related to each other. They have this linear relationship, residuals. UI is related to UG. But we don't want it. We don't want autocorrelation. So we don't want a linear relationship between the residuals. So to perform autocorrelation tests, we are going to use Debye-Watson test, and we'll use the Bruch-Godfrey-Lagrange multiplier test, LM test. Okay. First things first, I would get my regression output. By the way, guys, let me show you something. Let's say residual diagnostics. Let me just heteroscedasticity. Let's say I perform any test, I do anything. By the way, you know, this is my regression output, right? If I run my regression, this is my output. Now from here, I come to view, I can do whatever I want. I can check coefficient diagnostics. Maybe I want to check variance inflation factors. Residual diagnostic, I want to perform this test. Stability, I want to check Ramsey. You can do anything which will take you away from this output. So let's say I perform heteroscedasticity test, let's say Glacier, and I have my results. If I want to go back to my regression output, okay, what I can do is I can come to estimate, just come to estimate, and you see everything is here. And if I click on this OK, I get back my output, right? Or you can cancel all of this and then maybe come to quick and do it again. Or what you can do is residual. Let me just do something. Let me just say Glacier. I have this. I want to get my output. Come to view. You see an estimation output. Click on it and it takes you back to your output. So you can always come back to your output if you want. Okay. So this is my output. Now I'm checking autocorrelation. I'm using Debye. Autocorrelation is, who can help me? What's autocorrelation?
Is the connectedness, like there's a relationship between the residuals.
Okay, I'll answer you, but first of all, do you know what is correlation? That's the first thing I'll answer you. Do you know what correlation is? Yes. Let me show you something. There are two words. There's correlation and there's auto. When you combine correlation and auto, it gives you autocorrelation. So first things first, what is correlation? No, strength is one arm. There are two. Correlation is showing you, sorry? Yeah, association, I can accept it, relationship, but it's showing you linear relationship. Let's say I want to look for the correlation between two variables, X and Y. It means I'm trying to check the linear relationship between X and Y. This correlation will show me two things about this relationship. It will show me the strength and the direction. By the strength, what do I mean? Is it weak? Is it strong? Is it medium? By the direction, is it positive? Is it negative? But it is linear relationship. So it is showing me linear relationship between two variables, X and Y. It is showing me the strength and direction of this linear relationship. By strength, I'm checking if it is weak, medium, or strong. By direction, I'm checking if it is positive or negative. But it is between two variables, correlation. Now, if it is between one variable and itself, it becomes autocorrelation. So this auto simply means it is between me and me. If it is between me and you, it is correlation. But between me and me, it is auto. Auto means with itself. That's the reason why it is auto. So actually, this autocorrelation is actually correlation. But that word auto there is simply telling you that it is correlation between something and itself. So we are checking if there is correlation between residual and residual. two successive residuals, ui and uj, are they related to each other? If these two residual, if a residual is related, that is current residual and past residual, or previous and past, two residuals, successive residuals, are they related to each other? But it is the same variable. That's why they use the word auto. So autocorrelation, we are trying to check if there is any linear relationship, powerful linear relationship between the residuals, between successive residuals. Now, we don't want it. If there is this powerful linear relationship between the residuals, it means there is autocorrelation. But if it is not, it means there is no autocorrelation. Now, how can we check it? To check if there is autocorrelation or not, we can use Debye-Watson test. We can also use Bush-Godfrey LM test. This LM stands for Lagrange multiplier. Okay, but just say LM test, whatever. Now, let's start with Debye-Watson test. This Debye-Watson test give us the Debye-Watson statistic, test statistic ranges from 0 to 4, right? So Debye-Watson statistic will always be between 0 and 4. It cannot be above 4, it cannot be below 0, it cannot be negative. It ranges from 0 to 4. Now, between yes, I'm trying to write something. We have 2. If the Debye-Watson statistic is 2 or around 2, it means we conclude that there is no autocorrelation, right? But if it is far from 2, what does it mean? It means it is close to 4 or close to 0, because the two endpoints are 0 and 4. Those are the two endpoints. 2 is in the middle. If it is around 2, it means no autocorrelation. But if it is far from 2, which means either close to 4 or close to 0, then there is autocorrelation. One is positive, one is negative. I always get confused, but I'll check. Just give me a second. I think I wrote it somewhere. Which paper is that? I wrote it. Okay, I should just check from the internet. I always get confused which is which. Positive and negative. To correlation. Watson test. Okay, you see here, they say the Debye-Watson statistic always ranges from 0 to 4. At value of 2, it means there is no autocorrelation. Let me open this. I'm trying to check which is positive and which is negative. But I think, anyway, let me not guess. Okay, you see, the Debye-Watson statistic, my computer is slow, freezing. It's used to test for autocorrelations in the residuals from a regression analysis, right? It will always range from 0 to 4. If it is around 2, if it is 2, it means there is no autocorrelation. If it is closer to 0, that is less than 2, it means there is positive autocorrelation. If it is closer to 4, it means negative autocorrelation, right? So I always get confused which is positive, which is negative. But just know that if it is around 2, there is no autocorrelation. If it is far from 2, either towards 4 or towards 0, there is autocorrelation. Whether positive or negative, it means at the end of the day, there is autocorrelation. If you want to be more specific, if it is above 2, close to 4, you can say negative autocorrelation. If it is below 2, close to 0, you can say positive autocorrelation. But for me, what I just say is that autocorrelation. Then you can be specific if you want. Okay, let's come back. So, just know that it should be 2. So let's see our regression output. You see here our Debye-Watson statistic is 1.3, right? First of all, it is below 2, and it is it closer to 0, or is it closer to 2? Okay, it's below 2, and this is a problem with the Watson test, I'll tell you. So it's below 2, it's not 2, so we can say there is autocorrelation. Is it positive or negative? Let me see. Positive. So we can conclude that there is positive autocorrelation based on this test. But there is a problem with this test, David Watson. The problem with this test is that there is a zone of indecision. What do I mean by zone of indecision? It can be less than 2, but is it really close to 0? So we say that if it is 2, there is no autocorrelation, but if it is less than 2 and really close to 0, then there is autocorrelation. But how close to 0 can it be? For instance, if it is 1.5, 1.5 is less than 2, but is it close to 0? So we don't really know if there is autocorrelation, or we cannot make this decision, right? Same, and I think I explained we saw something like this in the slides. I explained it, right? Guys, we have 20 minutes. I'll close. I just want to show you what I mean. Okay. Let me get this slides. Oh my, oh, does somebody have a marker? I can write in the board. Guys, give me a second. My computer is messed up. It's slow.
I think if you want to miss some water.
I know why now. I know why it's slow. Can you not see how many pages are open?
Yeah, I mean the tabs. You should close a little bit.
And then look at Microsoft Word. Look at how many pages I have open Microsoft Word. So many. It's just.
I'm worried to say mashallah, but it will increase it.
Sorry?
Mashallah means make God increase it or give it more, you know. So I'm worried to say mashallah so that it will be more fast.
Yeah, but I'm rounding up with this regression today. Next week we should talk something else. You close the tabs. If I close it, it's going to make my life difficult. Now my life is easy.
So this means that you don't rest on that, you don't switch it off.
I never shut down my laptop. I just sleep it.
Oh.
It sleeps. I go to sleep. If I wake up, it wakes up. I shut it down.
But you can't use all of them at the same time. You use all of them at the same time.
You can understand.
I mean, you can save for example, for Google Chrome, you can save the tabs or like the links.
Yeah,
You can
it's not a matter of links. It's not the same tabs. The tabs keep changing. It's not like it's the same tabs. Once, so many things at once. You cannot understand.
Okay, you like that.
Yeah, that's how you get comfortable.
You cannot understand. No bother. With time, you will understand. All right. Ikra, are you now fasting? Are you now fasting? You should fast. Very soon, fasting period will be over. Fasting period will be over, and you have no excuse. So take advantage and fast. You are saying yes, sir.
I mean, maybe she doesn't want to let anyone know if she's fasting or not. You know, she's feeling it pure.
She's not fasting, I know. Not fasting eating. I saw the other day in the canteen eating. Somebody who is fasting will be eating. Yes. I saw you eating in the canteen. I'm not saying today. I'm not saying today. I say I saw you eating in the canteen the other day. Okay, this is the Watson issue, guys. Look at something. You see, it ranges from 0 to 4, right? And here we have 2. So you see, if it is here, if it falls, if it is 2 or around 2, we can say there is no autocorrelation. If it is here, this is inconclusive. We cannot make a decision. So we cannot say whether there is positive autocorrelation or not. If it is here, it's inconclusive. We cannot say if it is negative or not. Then if it is here, we can say for sure it is negative. If it is here, we can say positive.
But in this inclusive part, it's autocorrelation, but we can't say it's positive or not. Or we can't say.
No, we can't say if there is autocorrelation or not.
Okay.
Inconclusive. Okay. So because of these zones of this zone and this zone are zones of indecision, here we cannot decide. Here we can decide. So because of these zones of indecision, these inconclusive zones, there is a problem with the test. So you might get a Watson statistic which falls in these zones of inconclusion. So you don't know if you cannot say with certainty if there is autocorrelation or not, right? But if it falls here, for instance, you can say with all certainty that there is negative autocorrelation. If it falls here, you can say with all certainty that there is no autocorrelation. So that is one criticism of this test, Watson. Another criticism of this test is that Watson is that it shows us autocorrelation only at lag 1. Lag 1, which means first order. Which means if we have autocorrelation at more than lag 1, this test will not detect it. So it's another limitation. Those are 2 important limitations of the test. Because of these limitations, the Watson test is not the best test. It's not the best test for autocorrelation. So this is a better test, this one. So this Watson test is not really the best test. Of course, we also use it, but it's not really the best test because of the zone of indecision and also because of the fact that we cannot detect autocorrelation at more than lag 1. I can give you another limitation. With the Watson test, we need a high number of observations. Sample size should be really big. Okay, so because of this kind of things, this test, BG test, Bush-Godfrey test is a better test, right? It's a better test than Watson. So how should we perform BG test? Same thing. Once you have your regression output, come to view, still come to residual diagnostics, come to serial correlation. Serial correlation and autocorrelation in this case mean the same thing. You see there it is LM test, right? Serial correlation LM test. If I click on it, okay, now you see with this test, they will ask to specify the lags. So I can put 1, 2, 3, 4. I can check at different lags. But with the Watson test, it is only lag 1. It tells us autocorrelation only at lag 1. But with this BG test, you can have autocorrelation at lag 1, lag 2, at different lags. But again, while putting the lags here, you have to be careful. If your observations are not really many, sample size is not really big, don't put too many lags because you lose degree of freedom. If it is annual data, you can use maybe 2 or 3 lags. Monthly data, you can use maybe 12 or 13 lags. Quarterly data, you can use 4 lags. Okay. So I would leave, if use is suggesting that we should use 2 lags, so I will use what if use is suggesting. I will leave it at 2 lags and I'll click OK. So you see here it is Bush-Godfrey LM test, right? So just check this value. You see it is bigger than 10. Bigger than 10, what does it mean? It means we cannot reject the null. So we cannot reject the fact that there is no autocorrelation. Therefore, we conclude that there is no autocorrelation, right? So that's how we perform the test. Now we are done with residual diagnostics. Now we are going to see stability diagnostics. Stability diagnostics. Yes, it's something you have never heard since you were born. So you should be happy to hear it now. You have never heard it. Why are you laughing? Have you heard it before?
I heard the word stability and I heard the
word
diagnostics.
Yeah, but you have never heard Ramsey reset test since you were born.
Last week you mentioned. Not last week.
Okay, so you heard it once since you were born once,
yeah.
And now twice. Okay, guys, this is the last thing we'll do. Ramsey reset test. I will tell you what is happening in here before I perform the test. Now, the first thing I'll tell you about this test is that unlike other tests, for instance, if we want to check if we use white tests, we know that we are checking heteroscedasticity. If we use this BG test, we know that we are checking autocorrelation, right? If we use Jagbera test, we know we are checking multicollinearity. But the issue with this Ramsey reset test is that this test can be used to check many different things. It can, so don't feel that this test, we are only using it to check functional form. No, we can use it to check functional form, but we can use it to check many different things. Because of this, it is called a general test. Like they call it portmanteau test. So Ramsey reset test is a portmanteau test. This portmanteau means general. So don't feel like maybe this is the name of a scientist who created the test. Portmanteau simply means general. I'll show you something. Meaning of, how do you spell it? Portmanteau. I think it's an English word, right? Everything's slow.
Yeah.
Nothing is coming. No, it's because my laptop is freezing. I need to. It's tired. It needs to rest. You know. No. I cannot allow it to shut down.
Oh my God.
It should not shut down. Why should it shut down?
I feel sorry for you.
The laptop, I spent some good money to buy this laptop, so I have to deal with it.
Exactly.
It has to work the money. Yes.
For longer period.
I have to make sure the laptop depreciates well. It has to depreciate well. What?
You convinced him.
Why is this not coming? Problem with my browser. Guys, everything frozen. I pity this laptop. Okay, let me check a different browser. How do you know?
Because I think
You go there in? Okay. Yes, I'm a student in year is. It's surprising to so many people, right?
You are still in the nearest?
Yeah.
both in here and both in home.
Yes. No, I study in English. I can't find. Okay, it's not too important, guys. You can check. But as I know, portmanteau means general. Yeah, I'm studying in year is. By the way, guys, I'm doing 2 different PhDs simultaneously. So you can imagine my workload. I'm doing. In year 8, I'm doing PhD in business administration and year finance. So, making my life difficult. But okay. Sorry? Yeah. You know, there with them, their postgraduate classes are in the evening from 5, after 5. So whenever I close from here, I go there every day.
So basically, you are saying that nearest is easier to be able to graduate faster.
No, why? I've not said so. I didn't say so. I'm just saying that I live from here and I go there. That's all I've said. I'm not saying that one is better or this one is better.
No, I know. It's not about that.
It's not too difficult for me because I live in Nicosia anyway. So it's on the way to my house. So I close from here, go there, attend my classes, and then by 9 o'clock, I get home. By 8 o'clock in the morning, I'm back here. Shakeju, every day. Okay, guys, stability diagnostics. By the way, I saw you in the canteen eating the other day. So, Ramsey reset test, this is a general test which can be used to test many different things, right? So we are going to use it to test functional form. Okay, what do I mean by functional form? When you hear of functional form, think about linearity, non-linearity. So if you have a model, let's say ln CO2 is equals to constant plus beta 1 ln GDP plus beta 2 ln FDI plus error term. So this is a linear model, right? And we all know why it is linear, right? Because all the powers are 1. We don't have any power raised to the power 2. But if we have powers more than 1, let's say here was GDP raised to the power 2, that becomes quadratic, right? It's no longer linear. So if you have any power which is not 1, it means it's not linear. But you know, with ordinary least squares, we are using linear models, right? You know, according to Gauss-Markov theorem, we have blue characteristics. And what is blue? Best linear unbiased estimator. So it has to be linear. So we are using linear. Of course, we can also have cases of non-linear, but we are using linear. Now, when you use a linear model, when you have your model and you are doing everything, and you estimate your model and you interpret your results, you're just trying to be sure that maybe, trying to check to be sure if the functional form of your model is appropriate. Was it appropriate for you to use a linear model, or maybe what you're trying to, what you're investigating, the theory, maybe a non-linear model is appropriate, I don't know. So you're trying to check if your model is appropriate or not, the functional form of your model, is it appropriate or not? So we are using Ramsey reset tests to perform these tests, and these are the hypotheses. Null is telling us that functional form is appropriate. Alternative is telling us that it is not appropriate. So again, sorry guys. Again, let me call back my output. I have my regression output, right? Come to view, come to stability diagnostics, come to Ramsey reset test, and click. Again, you can specify the number of fitted terms, but always use the one Evius is suggesting. So I'll leave it at 1, and I have my results. Guys, when checking the results, check only this part. Forget about the down part. And you can check both C and F, but for me, always check F, right? Because you know F is a joint test, C is, yeah, so always check F. In this case, they are the same. So check F statistic. Don't bother about the test statistic because we don't know the critical value. Check probability value, 0.8, that's 80%, is bigger than 5%. Therefore, we cannot reject the null. So we cannot reject this null. And what is the null? Functional form is appropriate. If you cannot reject this null, therefore, your functional form is appropriate, which means your model is correct. So everything is fine. So you can see your model is stable. That's why it is stability diagnostics. Yes. Yes, we are checking if the model is stable or not. That's why it is stability. So functional form is appropriate. Therefore, it means our model is stable. The functional form is appropriate. So there is no what can I say? Okay, let's just say it's appropriate. Yes, you want to say something? Stable? No. We are testing if the functional form is appropriate. To check the stability of the model, there are many measures. Okay, I'll show you something. Look, stability diagnostics, right? Are you seeing? We use all these tests to check stability diagnostics, all. So Ramsey reset test is just one of them, right? So it is telling us if the model is stable or not, but it's not like it is the only test. All these tests, like for instance, Cho test, we can use a Cho test to check if we have structural breaks. We can use this recursive estimates test, things like Kusum squared. Don't bother about it, we'll see it with AUTOCORRELATION. But just with Ramsey reset test, it is one of stability tests. So all these tests are trying to check if the model is stable or not. That's why they are stability diagnostics. So all of them are checking if the model is stable, right? But in particular, with the Ramsey test in our case, we are checking if the functional form is appropriate or not. So in this case, what you can conclude is, if your problem is a wet stable, just conclude that probability value is greater than 5%, therefore we cannot reject the null, so our functional form is appropriate. I think it's fine to say it that way. But
what appropriate refer to? Like how we say that.
You know the meaning of appropriate?
I know what appropriate is in English, but
Yeah.
here, what do you mean?
It means our functional form is not incorrect. That's why, as a first step, you know, see, typically what people do is, you know, the way I was taught and the way many people teach this thing is that you do everything, like if you're writing a paper, you get your results, do all your analysis, do everything, and then at the end, you check diagnostics tests and you check all these tests. Actually, you are supposed to check these tests at the beginning. That is, once you get your data and you get your results, even before you start reporting your results and interpreting it, you have to check if there is normality, if there is no heteroscedasticity, if you have these problems, solve these problems first and make sure that these problems are no longer there before you can now get your regression output and you interpret your results. But most people will get their output and interpret the results first, then they will check these problems at the end. What if you check and you found that you have these problems? It means all your results are not reliable. You have to go back and change it. So if your functional form is not appropriate, then you cannot rely on this model. So you should not check this at the end. This should be checked at the beginning. If your functional form is not appropriate, then maybe you should specify a different model. You understand? Specify a different model which is appropriate before you can proceed. So typically they always check it at the end, but for me, I think it's good to check it at the beginning so that if there is a problem, you solve the problem, not that you do everything and then you discover a problem at the end. It means if your functional form is not appropriate, or if you have heteroscedasticity, your residuals are not normally distributed, it means everything you have done is not reliable. You understand? That's why most at times, I'm not supposed to be telling you this, but I'll tell you, most at times, so many people manipulate these results. Like they will report everything, report their results, and then at the end, when they want to check diagnostics, they discover that they have a problem. Now they cannot report this problem because if you report this problem, they will not publish your article. It means your results are wrong. So they will not report, they will report normality, but they will not say it's normal, it is not normally distributed. They will try to change the probability values, try to change the statistics, and report fake results because they decide, that's because they check the problem at the end. So me, I always check it at the beginning. If there's a problem, I solve it at once before I do my analysis. Understood? Sava? Okay. So I think that's all. That's all for regression. Let me stop recording, by the way. I'll just leave this place. So guys, we are done with regression as far as I'm concerned from my part. I don't know, with Nigaoja, with the slides, we did not finish it, right? So maybe she will try to finish it. I don't know. I will see her now if she's around. Is she around? No. She did not come today? I will try to, okay,